I know it's a long days, but we have one more long days to go. Okay, so we have a lot of exciting sessions today. Just to proceed to the program, so we'll be starting today with a talk by Zhao Zhang from Texas Advanced Computing Center. He will be talking about Stable-TopK. Then we have Professor Stan Tomov. He will be talking about Hefty and the Exascale FFT library. Then we'll have the keynote talk by Bronis Supinski from Lawrence Livermore National Lab. So he's the CTO of the Lawrence Livermore National Lab. He will be talking remotely. That's why we pushed him a little bit late so that he doesn't have to wake up very early in the morning in the West Coast. And then after the coffee break, we'll have the talk by Dr. Yifeng Kui. He will be talking about some of the extreme scale earthquake simulation. He's doing it in Rapid with the compression and all. We showed some results yesterday. Then we'll have Professor Hyunwook Jin from Konkuk University. We'll be talking about asynchronism in MPI intra-node communication. And we have Greg talking after that, maintaining the MPI deployment provenance with SPAC. And then after the lunch, we'll have Samuel Kuvis from Ohio Supercomputer talking about optimizing AMBER for device-to-device GPU communication. He has some nice results. The AMBER, if you convert to CUDA-aware MPI with MFAPIS to GDR, you get to see very good performance kind of things. He will be talking about that. And then we'll have Dr. Hyun-Woong An from ETRI, South Korea. We'll be talking about KNN accelerator using near memory processing and MPI technology. And then Mahidhar Tatineni from SDSC will be talking about experiences with MFAPIS and INAM on the San Diego supercomputer systems. So then we'll have presentations from Dr. Donglai Dai from Xscale Solutions. He gave a tutorial earlier, but today he will go into more details on all these different packages, performance numbers. And then after the coffee break, we'll have presentations from Dr. Kasper Cornett from University of Cambridge. They have started running some of the experiments on Intel GPUs, and that's what I believe he will be sharing some of the very early numbers here. And then we'll be having two tutorials. Hari and Poya will be presenting about the INAM. We talked about that a little bit yesterday. Some of you might be familiar how the INAM works. They will give a tutorial. And finally, we'll have a tutorial from Dr. Amir Safi on the high-performance big data stack, like the MPI for Spark, MPI for Dask. We talked. So we have a very packed agenda. One more thing, I talked to some of you in the morning. I think many of you are new to this campus. This is the main campus. After the morning coffee break, I can take some of you in a walking tour, okay? So those of you who are interested, just immediately after, towards the end of the coffee break, meet me. We'll just go for like a half an hour and then come back, okay? Sorry, I know it will conflict with Yifeng's talk, but since many of you are first time in the campus, I'd just like to show you how things are running, okay? Again, it is just optional. Whoever is interested can come, okay? So with this, let's start the today's the first presentation. Dr. Zhao Zhang, he's a computer scientist and leads the machine learning group in the data intensive computing group at the Texas Advanced Computing Center. Prior to joining TAC, he was a postdoc researcher at the AMP Lab, UC Berkeley, and the data science fellow in the Berkeley Institute for Data Science. He received his PhD from University of Chicago. He has extensive experience in the HPC and big data systems. His research focus is the fusion of HPC and deep learning with a wide range of topics of optimization algorithms, IO architecture, and domain applications. Even though the affiliation says TAC, as some of you know, he's on a transit. He has just joined as an assistant professor at the Rutgers University. So his affiliation is still old. So Zhao is new now in the faculty line. So Zhao, are you there?
Yes, I'm here. Hi,
okay.
DK.
Go ahead. Share your slides and then we'll see.
Yeah, I can't share right now.
I think something is not coming here correctly. Just give us a minute.
Yeah, sure.
You are not able to share?
Let me see. Yeah, nothing popped up. Okay. Oh, okay. Give me 1 sec.
Yeah, yeah.
It's a new laptop, sorry.
Yeah, while Zhao is setting up, he was supposed to actually come in person. So his things got shipped from Austin, and the shipping company decided today for the delivery in person. Okay, so just few days back he canceled his trip, so that's why he's talking remotely. So I hope, Zhao, you will get your stuff today on time. Restart the Zoom. Oh, oh, okay, okay, okay. Oh, I see, I see. Okay, okay. And now we can see. Make it presentation mode.
Okay, presentation mode, yes. This.
Yes, we are good.
Yeah. Hi guys. This is Zhao. I had to cancel my trip to Columbus in the last minute because like furniture delivering like an emergency, and now I have a flooded basement, so it's a mess right now. Yeah, but thank you DK for inviting me to give this talk. So this talk is about like a new gradient sparsification technique, and it's still in progress, which means we're still working on it. So rather, this is just a progress report. And okay, the title is Stable-TopK. We're trying to exploit like temporal stability of top K gradients. And this is led by DK students Quentin and one of my colleagues Minkai Attack, and in collaboration with Lang, Amir, Harry, DK, and myself. Okay. Ooh, nice. Okay. So why people are doing sparsity when training large foundational models? Because communication latency is the major bottleneck when we are doing distributed deep learning at scale. This communication overhead increases linearly with the size of the gradients and also the processor count, right? So the size of the gradient scales with the size of the model parameters. Like if we assume every single parameter is being updated in every single iteration, then the size of the gradient is equivalent to the model parameters, to the number of parameters, right? Specifically, if we are training with single precision, or half precision, there's a way for us to estimate the memory consumption and also memory assumption for the gradient, also the communication overhead. And large scale training usually requires single precision gradients, for example, in large and lamp, even though we can do half precision for feed forward and backward computation, but for gradients, we have to use single precision. And assuming using single precision, training like a BERT large will cost like 1.3 gigabytes communication per step. And if training GPT-NEO X 20 billion model, like this is a variance of GPT-3, it consumes like 74 gigabytes per iteration. And I mean, if we were training GPT-3 175 billion model, I mean, every single iteration takes consumes like 652 gigabytes communication. But like GPT-3 175B is not simply deployed with data parallelism, so that's a little bit different. Yeah, cool. So communicating gradients requires expensive networking and bottlenecks training, right? And however, gradient values are noisy, and most values are near zero. And from some previous study, if you look at this reference, we see a lot of the gradients are just zero. And only the gradients with large magnitudes really matter for training convergence. And but there's an open question: is how many gradient values can be removed from before convergence is effective, right? We want to improve the communication performance, but we don't want to downgrade the model performance, which is the convergence, right? So how much gradients can we throw away each iteration? That's an open question, right? So what is Sparsification? How Sparsification is usually done? So we can certainly reduce communication volume by only propagating some gradient elements, right? This is a very general statement, okay? And we can conceptualize a compressor function. The input of this function is all the gradients that we want to communicate, and the output is the gradients that we actually communicated, right? So there are a bunch of ways to implement this compressor, either through TopK method or using random method. There are a bunch of cases, but there are a bunch of methods. And this is just very general description. So this compressor function keeps only k gradient elements and sums and stores the remaining values as a residual for the next iteration. So this is to say, we're not simply throwing the smaller gradients away, rather we're accumulating them until they reach some threshold or the accumulated value is larger than some like the largest gradient values, we start to communicate them. So this is from deep gradient compression work from Song Han. Now he's a professor at MIT. So yeah, years ago. Okay, cool. So the TopK compressor function selects the top K largest elements, in terms of magnitudes of the gradients, and accumulates for all other elements. And TopK method has commonly been implemented at the Python layer, and has been added to native PyTorch. Okay, and convergence has been proven and demonstrated for many model types, but requires careful hyperparameter tuning. Yeah. So gradient Sparsification methods have been studied comprehensively by many groups. Yeah. Okay, sorry. We have a slide that summarizes all the related works later on, so just bear with us right now. Yeah. So how does TopK sparsity works? So in dense data parallel training, the full gradients are averaged across all workers by our reduced operation, right? I mean, if we use the bandwidth optimal reduced scatter algorithm, this communication overhead increases linearly with the number of processors, increases linearly with the model size, right? And the TopK sparsity works by applying a Sparsification GPU kernel on each worker, then communicating the positions and TopK values via a sparse all-reduce operation. It can also be done with the all-gather P operation if you are familiar with MPI. So looking at the figures on the right-hand side, okay, so this is a simplified SGD rule, right? So we just updated the parameters with its previous value minus learning rate multiplies the gradients, right? And on each GPU, we have a identical copy of all the parameters, and we run the forward backward computation. Oh, where's my mouse? Oops, sorry. Yeah. So once we have the gradients, we can call it all-reduce to compute the global average of all the gradients. Then we can update this parameter, right? This is the traditional SGD. But with gradient methods, here is additional TopK GPU kernel. Here we select let's say we are selecting 1% of the gradients. Then each GPU will select its own local 1% top gradients. And then we need to communicate those gradients to a single place to select the global TopK threshold. Then we send this threshold back to every single GPU to do its filtering. And then we do a all-gather P to collect all these gradients that are within the range of 1% of magnitude. So this is how it works. It's actually two steps. First, we have to decide a threshold. Second, we need to communicate those gradients, right? Okay, so the previous state of the art of work includes like the deep gradient compression. So this DGC attempts to resolve the hyperparameter tuning problem by TopK sparsification of gradients, and this modifying the optimizer and the gradient update rules to correct sparsity convergence effects. And they use this to push the sparsity to 99.9%, which means they only communicate 1 out of 1,000 gradients in each iteration. But the downside of DGC is it doesn't help much when interconnect is fast. So DGC assumes the network, the interconnect is less powerful than what we have seen. What we are using on a supercomputer, and it also introduces high GPU cost in selecting gradients, and it doesn't quite scale when the communication overhead dominates the whole training time. And the right two figures shows this trend. Okay, and so Thorson proposed a method called OK-TopK maybe 2 years ago. So so they claim this is a near optimal solution for sparsification. And okay, so if we look at the sparsification overhead using the alpha beta model for millimeter with an MPI or communication, right? So the sparsification overhead scales with the number of processes P. The cost of sending message of size L equals alpha plus beta multiplies L, right? And where alpha is the latency, beta is the bandwidth, L is the time cost per data unit, per volume unit, right? And there are a bunch of methods like the dense, which is the standard already used algorithm to compute the average. There's TopKA, which applies altogether and local sparse reduction. TopKDSA, which is Spark CMLs, sparse reduce scatter and altogether communication. And GTopK uses this reduction tree and broadcast tree mechanism. And the Gaussian K, same as TopKA with Gaussian fitting. So Gaussian K assumes the gradient distribution is with a Gaussian distribution. So they try to estimate this distribution with some sampled gradients, and then they decide the top 1% threshold. Okay, and the OK-TopK splits buffers via SN and I receive, and doing sparse reduction and using altogether V to gather all the gradients. And the right-hand table shows the bandwidth and latency for cost for each of the communication cost with bandwidth dominated terms and latency dominated terms for each of these algorithms. And from this analytical comparison, you can see OK-TopK the overhead doesn't depend on P, because when P gets larger, this P minus 1 over P just simply cancels, right? And only the latency part scales in logarithm with P. Okay, so yeah, so ideally OK-TopK should scale pretty well. And a secondary results from the OK-TopK paper is they profile the BERT gradients in the BERT application are also sparse. Okay, yeah, but there are some shortcomings. There are shortcomings of this OK-TopK solution. So while it's scalable, it really hurts convergence. It doesn't converge. We use we run language models have two measures of accuracy. One is what OK-TopK has been used in the paper is showing the training loss as perplexity. Okay, so it's the accuracy while model is training on general language data. But really, people cares more about the downstream evaluations. There are standard benchmarks for BERT. And as we show in this table here, we use the SQUAD V1.1 benchmark and also the GLUE benchmark. So the GLUE benchmark includes if I remember correctly, it's maybe 8 or 10 downstream tasks, and GLUE simply represents the average of all these performance of all these tasks. So while the OK-TopK paper demonstrated reasonable training loss, our experiments, so we retrain BERT using their methods, and the experiments show poor downstream evaluation accuracy. If you look at here, the SQUAD baseline is 90.4 in our case, but with OK-TopK, we can only achieve 88.1. And for GLUE, the baseline is 0.802, with GLUE is only reaching 0.77. Okay, so this motivates this opens the opportunity for our research. We seek to find a gradient sparsity strategy that is scalable and also preserves the downstream task performance. We don't want to lose the model performance. Okay, so what we have been observing by looking at the gradients of BERT, here's what we observe. We hypothesize that gradient elements are temporally stable because pre-training should lead to the creation of circuits that are comprised of nearby neurons. and such circuits should gradually adapt over many training iterations. So which means as long as the training proceeds, the gradients are more like fine-tuned rather than significantly changed, including their magnitudes and also their positions in the tensor. So we found this hypothesis to be true for ResNet 50 and also transformers. We tried BERT large, OpenFold, and Vision transformer. And the right-hand figure shows the first attention layer of BERT. The vertical axis is the positions of the gradients, and we are using a bucket size of 10,000. So each point here is actually 10,000 gradients, and the horizon axis is the time. So this is showing BERT training, phase one of BERT phase training. Phase one of BERT training, and you can see the gradients within the top 1% range stays fairly stable across time, right? And we can see clear bands over here. So we observe that regions are stable, but the individual gradient positions are not. If you look at the figures here, the two figures, I mean, if we use bucket size of 10,000, they're quite stable. But if we're using individual positions, like here, it's not stable because it keeps changing, but they change within a certain range. Okay, so such behavior necessitates the use of a TopK bucket instead of specific elements. And these insights introduce the key idea of our work. So instead of communicating the exact TopK elements every iteration, we only communicate TopK buckets every n iterations. So there are two key hyperparameters. One is the bucket size, right? So here we are just showing a bucket size of 10,000. And there's a second hyperparameter is that the frequency of computing the TopK gradients is the n iterations, okay? Cool. And we also analyze the autoencoder code, which is a variant of Vision transformer, which you can see here. Then this is one of the attention layer in MAE, and you can see clear bands here if we use the bucket size of 10,000. But if we do individual indices, I mean, it's spread across all over the places, right? There isn't a clear pattern. Cool. So to implement Stable-TopK, the Sparsification kernel is only applied every n iterations. Like I said, because we assume it's stable, and we only update these buckets that we're communicating every n iterations, and communicating buckets of indices and their values instead of specific indices. And for all other iterations, simply apply the bucketed mask from the last recomputation. If you look at the figure right hand here, once we compute the gradients on each GPU, we decide if we'll check if we should update the gradient map, the gradient buckets that we should communicate. If we don't, we just use the previous bucket size to communicate. In this case, bucket size, we only communicate those like 6 gradients in this tensor, right? So in this way, we eliminate a lot of computation in deciding the gradient thresholds, and we are also eliminating a lot. So primarily, we're reducing the time cost in finding the gradient threshold. Okay, cool. And how does it really work in training, right? So we're varying Stable-TopK bucket size and sample frequency, and then we get some valuable insights into. And this is with BERT, okay? And again, the horizon axis is the number of steps. The vertical axis is the training loss. The blue line is the baseline, and the red line is the OK-TopK measurements. Okay, so if Stable-TopK bucket size is too small, for example, if we use bucket size of 1 and iteration frequency of 100 steps, you see this yellow bar shoots out, right? So this goes too far away. But if as stable sample frequency is too high, the stable region may decay before the Stable-TopK bucket indices are updated. Okay, so this is with the pink line here, stable. We use bucket size of 1,000 and iteration of, and we communicate for every 1,000 iterations, right? So this goes away because this doesn't track the change in the bucket the distribution. Okay, so there requires a hyperparameter finding phase, and if we can choose a appropriate bucket size and communication frequency, for example, this green bar, this green line, like with bucket size 1,000 and frequency of 50 steps, you see the training loss is pretty, close to the baseline, right? Okay, so for both BERT and MAE, Stable-TopK trains in shortest time, like we compare the time. I have numbers later on. And if you look at the figure, upper figure, you see this orange bar is actually what we have with Stable-TopK using a bucket size of 1,000 and a frequency of 50 steps. Okay. And also for this lower figure, this is for MAE, and this green line is actually the Stable-TopK with bucket size of 200 and the communication the gradient update interval of 50 steps. Okay, so yeah, so how does it perform? So since S-TopK doesn't compute the TopK indices every iteration, its throughput is higher than OK-TopK. And in addition to maintaining a low training loss, OK-TopK, Stable-TopK preserves downstream evaluation performance, but not perfectly. Okay. Again, if we can, so the left table shows the BERT large performance, and if we see squat, OK-TopK is only like 88.1, and with Stable-TopK we can reach to 89.96, which is very close, which is closer to the baseline, but we are still a little bit further away. But for glue, you see it matches the baseline, which is an encouraging sign. And in terms of time, baseline takes 84 hours, OK-TopK takes 52, and Stable-TopK only takes 42 hours. Okay, so it's almost like 2 times reduction from the baseline and 20% improvement over OK-TopK. And if you look at MAE on the right-hand side table, the baseline performance of the ImageNet, I think this is accuracy, the baseline is 84.1%. And with OK-TopK, you only get 81.3%. But with Stable-TopK, we get 83.8%. We are still like 0.3% away, but like we can reduce the time by almost half, right? Like almost half of the time. Okay, so it's challenging. It's really challenging to ensure convergence for existing methods, for example, like this OK-TopK method, right? And we find out like gradient indices are not stable over time, but the regions of the gradient elements are stable. So we deploy this, we design this Stable-TopK method and exploits this property by communicating sparse gradient regions periodically, and the Stable-TopK converges like much closer to baseline. It's not perfect, but it's much closer than competing sparse methods. It allows time for both BERT and MAE. And we are continuing the work on fine-tuning the hyperparameters to improve the convergence. We hope our methods will reach the same level as the baseline. So yeah, then we can submit a paper. Yeah, thank you. And you can send questions to my email. The tag email address was my old email, and the Rutgers one is my new email. And yeah, as DK introduced, I'm moving to Rutgers as assistant professor. Yeah, so thank you. I can take questions now.
Any questions for Zhao? Are there any online questions?
I don't see any.
Yeah, here we have one question.
Sure.
Zhao, very nice talk. This is Amit from SDSC. Just a quick question.
Hi.
What kind of systems did you run these experiments on?
We run this on Lone Star 6. And Lone Star 6 is so on each node we have 3 A100 GPUs, and we have like 72 of them, and they're connected with InfiniBand. And I believe Quantum also ran on the stability AI machine, but like we lost like access to that machine after some time period. And I'm not sure if the MAP version that we are using is available on other machine, but I would definitely like to try it on Promoter or Polaris in DOE and also the machine in SDSC. Yeah.
Okay. So what are the is it like TensorFlow or PyTorch and
This is PyTorch. This is like PyTorch based.
Okay. Okay. Yeah. Anyway, we can explore what if its software system matches. You can try on other machines also.
Yeah. Sure.
Thank you.
Thank you.
Yeah. One more question.
Hi. Actually, it's nice talk. One thing I'm wondering whether you have any general guidelines on how do you select the strike, because when you said the patch length or training length is one, you basically diverge. And
right.
One with some of the data set, if you don't select the update frequency enough, then whatever you reference to after I think it's 1,000 iterations or something.
Yeah, it will shoot out. Yes.
Basically diverged, right?
Yeah,
But
you're right.
That sounds like depend very much on the data set you are using.
Mm-hmm.
Is there any general guidelines that you can intelligently select that parameter so that you guarantee even for a unknown data set, you still somehow can get a reasonable approximation of a convergence solution?
This is a really, really good question. May I know who is asking?
Yeah, this is Dong Dai.
Okay. Yeah, this is a very good question. So far we are still in the research phase. We're designing sparsification methods that make it more effective. I think the next step will be to design a adaptive and self-driven. Maybe we can design an algorithm that starts with some predefined hyperparameters, and we observe how the training goes. If the training doesn't go well, we can adjust these hyperparameters. Make it self-adaptive. So this is a very good question and very important to the success of this method. Yes, these will be our next steps.
Okay.
Yeah. Thank you.
Any other questions? Yes. One more question.
Yeah. My question is the cause for instability, is it the learning rate or is it the numerical instability for which even actually reducing the learning rate would not help? So that's my.
Yeah, reducing the learning rate is more about the optimization side of things, right? So applying sparsity, there are previous work that proves that using sparsity is fine for convergence in theory, but in practically, nothing really works for the models that we are working on. So I think it's complementary. Adjusting learning rate may be complementary to this end. But if we are losing information in the integrity of the gradients because we're doing sparsification, yeah, it's worth researching. Yeah, we can. So we said in TopK methods, we communicate the largest gradients, right? But for the smaller gradients, we're accumulating them. And that is equivalent to applying a smaller, that is equivalent to accumulate, let me think about that. So working on more gradients, more iterations, this larger batch. So essentially that's the larger batch and the smaller learning rate. Yeah, I think theoretically we're applying two types of learning rate here. So for the largest gradients, we're applying a regular regular learning rate. But for the smaller gradients, because we're accumulating them, and when they are actually being communicated, it's a very, very large batch size. And I think that's equivalent to a smaller learning rate. Okay. Does that explain that?
Yeah. Yes.
Okay. So might be we can do a follow-up with Zhao by email. So let's move to the next talk. So thanks, Zhao.
Thank you.
Okay, not the next one. So let's move to the next talk.